Education in collaboration with Saibono Discovery Center. All right, great job. Today, our knowledge area, we are going back to doing mechanics as we were doing in first term, if you remember them. We are doing mechanics again today, and our topics of the day. Today, great job, we're going to try to squeeze in 3 topics in one lesson in preparation for the upcoming June exam. So we'll try to squeeze in and sort of revise these 3 topics in one lesson, which is elasticity. We'll also look at viscosity, and then we'll try and look at hydraulics. Try to see how we can collect marks during an exam with these 3 topics, which I believe these are free marks for us, grade 12. All right, so without wasting any time, let's go straight to our lessons. Our lesson objectives for the day is that by the end of the lesson, we are expected that we are able to define the term stress, we are able to define the term strain, we are able to state Hooke's law, we are able to calculate the stress, the strain, and the modulus of elasticity of a solid object. We are able to define viscosity. We are able to discuss the effect of temperature on viscosity. Effects of temperature on viscosity. We are able to state Pascal's law. And then we are able to use this Pascal's law to calculate either the force, the area, or the radius of pistons. So this is what we are expected. It might seem like a lot, but we'll take you through each grade off. Okay? Right. So things that I need you to make sure that you know before we go into this lesson, or things that we must just remind ourselves of, is that people, we must be able to give or even write down formulae for area or formulae for areas of the shapes, such as the circle, the rectangle, and the square. Grade 12, I cannot stress this hard enough. You must be able to give these areas or know the formulas for area of these shapes. The circle, the rectangle, and the square. And if you already know the circle, the rectangle, and the square, just to be safe or in a safer side, also know the triangle. Okay, this one has never been asked before, never come across a solid that was a triangle. However, in the exam guideline, it does not say that they will never ask a question where the solid is a triangle. You must be able again to convert from millimeter square to say, if I have a square millimeter now, the area of square millimeter to square meters, and also square centimeter to square meters. Some of this prior knowledge, grade 12, is not prior knowledge that you have learned in technical sciences, but it's prior knowledge from other subjects such as mathematics, the like of the area of the circle, the rectangle, the square, and even the triangle. And also the conversion of square meters to square millimeters to square meters, square centimeters to square meters is also a prior knowledge that you are expected to know from our subject, the neighboring subject, technical mathematics. Okay, right. So just to ascertain if we know these things, we'll just ask these a few 3 simple questions. Grade 12. I'll ask you to just quickly write down the formula for the following area, or for the area of the following shapes. Just write down for me the area of a circle, write down the area of a rectangle, write down the area of a square, the formulas. Right? Write down the formula for the area of circle, the area of a rectangle, the area of a square. And I want you to see that you are able to do that. And just once you are done doing that, just quickly convert for me 500 millimeters to SI unit. And we know the SI unit for distance is meters. Okay, so it means you are converting millimeters to meters. You are converting, and please also convert 20 centimeters to meters. I want to see if people are able to do those conversions, because those are important for today's lesson. Okay, also convert 4 square millimeters to square meters, and then also 8 square centimeters to square meters as well. And I want to see if people are able to do that. But then we'll go through each together just to remind each other of the important things there. Okay, so the area of a circle is given by the formula pi r squared. Okay, it's actually written like this: area is equals to pi r squared, where the pi is just the value which is 3.14 and some digits after that. And the radius stands for, R stands for the radius of the circle. It's the radius of the circle. So the formula is given by area is equals to pi r squared. Now, before we can even continue with the lesson grade 12, I also want to bring to your attention that writing pi as 3.14 is a complete no-no, because we are using scientific calculators to calculate. So I always advise learners to don't write pi, never write pi as 3.14. Pi is a value, but pi is also in our calculator. So whenever you want to calculate and using pi, just go press it on the calculator, second function, and you will see that there's a pi value there on the bottom button there, which says times 10 to the power x there. So please use the pi on the calculator and do not write 3.14. Okay, the area of a rectangle is given by the formula. Area is equals to length times breadth. Length times breadth, where you look for the length of your rectangle and the breadth of your rectangle, multiply both of them, you should get the area of a rectangle in square meters. Okay, and then the area of a square, its area is equals to side square. So you only need one side of a square to be able to calculate the area of a square. Area is equals to side square. Okay, and the area of a triangle, if ever it was to be asked for safety reason, let's write it down and let us be familiar with the area of a triangle. Half base times a perpendicular height. Half base times the perpendicular height is the area to calculate, or is the formula to calculate the area of a triangle. I will say I have never seen this one, a solid object which was a triangle. However, nowhere in the examination guideline does it say they will never ask it. So we must make sure that we are prepared, because in the examination guideline, you are not going to get these areas there. These areas again, or these formulas again, grade 12, are not given in your data sheet at the end of the question paper, paper 1. These formulas are not given. This is why I'm emphasizing their importance. It is important that we know them, and we know them by heart, because they are not going to be given. You must just know them and use them. You are expected to know them again from when? From technical mathematics. Not only technical mathematics, you are expected to know them from even primary school, where you've started learning about area, if not grade 8. From there, you've been learning area, so the expectation is that by now you should know the formula to calculate the area of any shape, okay, or simple shapes. Let's put it like that. So you are not going to be given these formulas. You are not going to be given area is equals to pi r squared. No one is going to give you area is equals to length times breadth. Area is equals to side squared. Area is equals to half base times the perpendicular height. You are not going to get that. It's important that you know it, okay? Right. The next question there was asking you to convert 500 millimeters to 500 meters. Okay. So how I convert grade 10 is that I always do the multiplication whenever I convert. I don't convert by sometimes multiplying and sometimes dividing. I always multiply by times 10 to the power something, whether it will be a -3 or a -2. I take this from again grade 10, where we were taught those SI prefixes that I spoke of also last week, to say if someone says 500 millimeters, then I'm talking milli, and the SI prefix of milli is times 10 to the power -3. So I simply need to take this value, multiply it by times 10 to the power -3. However, grade 12, if you have been taught to say 500 divided by 1,000, you should still get the same answer. So if you've been taught like that and you are comfortable with that, I advise that you stick with what you've been taught. Please stick with what you've been doing in class as long as it is working. Okay, so to convert from 500 millimeters to 500 meters, I will say 500 times 10 to the power -3. Some people will say 500 divided by 1,000. At the end of the day, we should all get 0.5 meters. Okay, let's convert from centimeters to meters. It was 20 centimeters. So 20 to me, that is times 10 to the power minus 2 centi. From the word century, century meaning 100. Some people will say 20 divided by 100, which should also give what? 0.2, as I also got 0.2 here. Okay, so that's how you would convert going from centimeters to meters. This is how you would convert going from millimeters to meters. Very, very important. If you lose these basics, you are not going to be able to win this, because this is a very, very simple topics, or topics that you are going to be looking at the grade 12. All right. And then number 4 there was saying, or question number 3 was actually saying to us, let's convert 4 square millimeters to square meters. Okay, now we are converting. So when I was converting from millimeters, I was saying times 10 to the power minus 3. Okay, now I am converting the square of this. It is the square of this, meaning that I am squaring the times 10 to the power minus 3. So it's minus 3 all to the power of 2. And if you remember from grade 9, again, your mathematics, how you multiply your laws of exponents. If I am squaring this, the laws of exponents says to me, if a to the power n all to the power m, this is equals to a to the power of n times m. Those are the laws of exponents, if you remember that. So that means I should just simply multiply the 3 times the 2 to convert there. That will turn to times 10 to the power of negative 6. So when I convert square millimeters to square meters, I will multiply by 10 to the power of negative 6. And then I should get my answer there. I could leave the answer is 4 times 10 to the power minus 6. It's already converted if you write it like that. Or you can press it in the calculator and get the ordinary value, because this is scientific notation, which would remember again we dealt with in grade 10. So this is written in scientific notation. This is just in ordinary numbers. Okay, so you can decide. You can just write 4 times 10 to the power minus 6, leave it like that, and write square meters as your SI unit. Okay, right. We're also expected to convert from square centimeters to square meters. So if I go from square millimeters to square meters, I multiply by 10 to the power minus 6. Okay, whatever the number is, I must multiply by 10 to the power minus 6. Now, I'm converting from square centimeters and I want to go to square meters. What should I do? I must multiply whatever the number is by 10 to the power of minus 4. Why minus 4? We are going from centi, which was 10 to the power of minus 2. But remember, I am squaring that centi, meaning I'm squaring because the area is always squared, right? It's a side squared. This side times this side. You're always squaring when you are calculating area. So if I square that, that is the same as saying minus 2 times 2, which is going to give me 10 to the power of minus 4. A to the power n all to the power m is the same as saying a to the power n times m. Exponential laws. Again, grade 12 was just talking about baseline information there, things that we are supposed to know already. So you can write that value there as 8 times 10 to the power minus 4, or you can write it in ordinary values as 0.0008 square meters. You can choose which one you are using then. So again, I want to emphasize the importance of knowing these formulae for calculating the area of this shape, the circle, the rectangle, the square, and also the triangle. And also I want to emphasize the importance of being able to convert from millimeters to meters, from centimeters to meters, from square millimeters to square meters, and from square centimeters to square meters. Very, very important. All right. Okay. So let's look at our terminology for a day. Grade 12 is a lot of terminology. It's a lot of terminology. However, it's nothing difficult, and it's things that you can know. By the time you go to write the exam, you can know this. People have done it before. Okay. It's not that difficult. It's a lot, yes, but it's not difficult. So that means you must start working on it as soon as possible. All right. So we'll look at forces such as deforming force, And we say deforming force is a force which changes the shape and size of a body. It's a force which changes the shape and size of a body. Remember, we'll be talking about elasticity. So we'll be talking about the shape and size of a body changing due to that elasticity. We're also going to look at elasticity as the property of a body by virtue of which the body regains its original shape and size when a deforming force is removed. So when things are being elastic, you think of a spring there, right? When you stretch a spring, right? When you remove the force which deforms the spring, because when you stretch it, it deforms, it loses the shape. So when you stretch it, it deforms, loses the shape. If you let go and remove the force that was causing the deformation, what is the spring going to do? It's going to regain its original shape and size. Okay. We'll also talk of perfectly elastic bodies as a body which regains its original shape and size completely. The word there in this definition taken from the examination guideline grade 12, the word completely is a key word. Okay, some bodies will regain their original shape and size, but they do not regain them completely. Only the one that regains it completely is considered to be perfectly elastic. Some bodies are just elastic, not perfectly elastic. See, when you are elastic, you regain your original shape and size, okay, when the deforming force is removed. However, if you regain it completely, that means you are a body that is what? Perfectly elastic. And a perfectly plastic body is a body which does not show a tendency to regain its original shape and size when a deforming force is removed. So we'll also be looking at perfectly plastic bodies. Okay, in this case, when we talk plastic, we're not talking plastic, the synthetic material, we're talking the type of a body. Does it regain its original shape and size? In this topic that we are looking at, when an object does not regain its original shape and size, we say it is now plastic, not plastic, the synthetic material, I repeat. Okay, and then we're also going to look at elastic limit. Okay, and we're going to say the elastic limit is the maximum force that can be applied to a body so that the body regains its original form completely on removal of the force. Okay, so all objects are going to have that elastic limit where you will stretch if you are stretching, or you are going to compress it to a point where it is no longer going back into its original form or original shape and size. We would say that object has reached what is called its elastic limit. Okay, all right, so we continue with our terminology. We also look at Hooke's law. There is Hooke's law there, which states that within the limit of elasticity, stress is directly proportional to the strain. That is Hooke's law. Very, very important to know as well. We will spend some time talking about Hooke's law there. Stress, an important definition to know, a very, very important definition to know, grade 12, the internal restoring forces per unit area of a body. And also strain, the ratio of change in dimension to the original dimension. Say something is being strained if its dimension changes, okay? You are straining it if its dimension changes. It was 4 meters, you compressed it to 3 meters. You have strained that solid object because it has changed its dimension. It was 4 meters, you stretched it to 5 meters, you have strained it, it underwent strain. There is a ratio of change in dimension there to the original dimension, grade 12. All right, then we're also going to look at viscosity. We've looked at viscosity before. You would remember when we were talking intermolecular forces in chemistry, or when we were doing the chemistry part of technical science. Okay, we looked at viscosity there. We said it is the property of a fluid to oppose relative motion between the two adjacent layers. That is the formal definition, and that's the definition that must always be written down if the question arises to say define viscosity. But you want to think of viscosity as sort of the resistance to flow of a fluid. How much does it resist? You remember we spoke about this. How much does the liquid resist to flow? Because we'll be talking liquid here. How much does the liquid resist to flow? Does it take time to flow, more time to flow, or does it take less time to flow? If it takes more time, then we say it's more viscous. If it takes less time, then we say it's less viscous. lot of examples that we talked about this last time. Okay, we're also going to look at a force called the thrust force that maybe most of us are not aware of, because we've spoken about forces before: your normal force, your force of gravity, your frictional force, tension force, but never have we ever talked about a force called the thrust. Okay, today we're going to talk about a force called the thrust. What is the thrust? It's a normal force. It is a normal force, but it's a normal force that is a special type of a normal force. It is one that is exerted by a liquid at rest on a given surface that is in contact with it. All right, and then we're also going to look at pressure. Pressure is another terminology that we must familiarize ourselves with when it comes to these topics. Pressure is the thrust acting on a unit area around a point. So that's why we have to talk about thrust, because we can't talk about pressure without talking about thrust, because pressure is as a result of what? Of thrust. It is the thrust acting on a unit area around a point. We will then finally look at Pascal's law, which again comes from thrust, pressure. Then we looked at Pascal's law, which is the application of this pressure that we will be talking about there. Pascal's law states that in a continuous liquid at equilibrium, the pressure applied at a point is transmitted equally to the other parts of the liquid, that liquid that was at equilibrium. We'll speak more about it when we get to this point. Okay, let's continue. So let's go right ahead and look at stress and strain. Sort of look at the summary of stress and strain, as again we've been speaking about the issue of time here. So we're going to say stress, again we've defined as the what? The internal restoring force per unit area of a body. And we say strain is the ratio of change in dimension to the original dimension. So what happens here? What happens here, grade 12, is that we have solids, okay? We have solids here. These solids will maybe be put under load, where a load is probably hanging, okay? Let's say you have a rod here that is mounted, right, on some roof, okay? And this rod is carrying a very heavy load, all right? There is load that this rod is carrying. Remember, this rod is solid. It's a solid rod, okay? It could be any shape. It can be a square rod, it could be a cylindrical rod, okay, or a rectangular rod, okay? Let's say it's cylindrical. It's a cylindrical rod here, and it's carrying a load, okay? So what we are saying here, or what it's being said here, grade 12, is that this rod will experience elasticity, okay? Or this rod is elastic, okay? This rod will experience something called the stress, okay? Why is this rod experiencing the stress? Because there is a force that is acting on this rod, okay? But this force is acting on a particular area, a particular point, okay? And this load here will cause this rod to extend, okay? The extension that will happen here, grade 12, will be very, very small, okay? But it is significant, okay? Because over time, this rod will extend. It will extend because this load here is heavy on the rod. So that extension that will be happening here, this rod extending, no matter how small it is, that extension, we call it what? Elasticity, okay? That it will be losing its shape, its original shape and size, because of the load that is put on the rod, okay? We will say that this rod is elastic if we happen to remove the load and the rod goes back to what? To its original shape and what? And size. If the rod does not go back to its original shape and size, we will call the rod what? Plastic, okay? But at the end of the day, whether it was elastic or plastic, by the mere fact that there is a force acting on it and on a particular area, this rod will stay experiences what? Experiences stress. The stress that we are talking about here is not the stress in general terms, okay? But if I can make an example of a stress in general terms, what causes stress in general terms? Or what is stress in general terms? Well, in general terms, you say you are stressed when you are sitting down and there are things that are you're just something that is eating you up inside. And remember, this is general language we are using here. Something that is eating you up inside. You're thinking. So it's sort of like there are forces that are within you that are making you to think that much. Okay. So whether, even though that's not the scientific way of thinking about it, you can also use it to understand the stress, because this stress is also internal restoring forces. So we're saying within this rod here, there will be internal restoring forces, such as the things that are causing you to think. Whatever you went through the day, to say, oh, I shouldn't have went through that. I shouldn't have done it like that. I should have studied. Okay, this is why I failed my test. I should have studied. These are things that are stressing, and they are within you. That is why we say stress is the internal restoring forces. Those forces are within the solid object, whether the solid object is a rod or whatever the solid object is. They are within the solid object. They are trying to restore. Okay, they are trying to restore the object. They are trying to oppose whatever the load is causing. So you are stressed because you failed that test that you were writing. That's the outside load that is coming. So inside you, there are things that are trying to restore that. I'm trying to make general stress to fit with the stress scientifically, great talk. I hope you're moving with me there. So inside you, you have these things that are trying to make you, to restore you. So they're making you think harder and harder. This is almost the same thing that is happening. There are forces that are trying to restore, fight against the load that is coming. So those forces, we call them stress. Those imaginations that you do, those thinking that you do, or whatever things that are coming in your head, in general terms, we call them what? Stress. Okay? So the outside load that is coming, we call it the force. Okay? Because this stress, the magnitude of the stress that a solid object can experience, we can calculate, great. Okay? So those external load, the external load that is coming, that's the force. That is the forces that are acting. Okay? But these forces, when it comes to solid object, they must act on a particular point. And that particular point, we call it the area. It's the area where the force is acting. Okay? That should be simple enough, Rachel. It's the area where that particular force is acting, and the particular force causes the stress. So there's an external thing that is a force, okay? And it acts over a certain area. And when it acts over a certain area, it causes the stress. What is this external thing in terms of the general language? It's the test that you failed. This test that you failed is acting on you there, causing you to be what? To be stressed. So do not fail this test, grade 12. Study and study hard and make sure that you are not stressed. Do not have loads over you there. Okay? So this is how we then calculate the stress, by using that force that is acting. And we know that the force, grade 12, is measured in newtons. Okay? That's the SI unit. We know this from mechanics first term. Okay? What about the area? We've just spoken about area there, and we should know from previous grades that the area is measured in square meters. So this will then lead us to the SI unit for stress. The SI unit for stress is Newton per square meters, because it's Newton over the square meter. So it's Newton per square meters. However, there is another SI unit that we can use for calculating stress, for the calculation of stress, and it's called what? Pascals. PA for Pascals. Generally, I like to use Pascals, simple for me to remember, but it is also important that you know, or you are aware of square meters, as it might be a question in the multiple choice question. Okay, the multiple choice questions, they like asking this question where they will say, the unit Pascal is equivalent to which unit, and they give you options, and one of the options is Newton per square meter. So being aware of it is very, very important. All right, now great job. Let's talk about this symbol. Writing this symbol is not easy, okay, for everyone, for all of us. However, let's refrain, great job, from writing this symbol like this. This is not an S or an integration symbol. This is sigma, okay? Let's refrain from writing it like this. Let's try to write it at least something like this, okay? Sigma symbol is equals to the force over area. Most of you just write the symbol like this as if you are writing a big S or you're writing an integration symbol there. That's not what we're doing. We're trying to write sigma. This is the symbol for stress. So it's important to try and write it correctly. Okay? Now, let's go back to our general knowledge then. Once you are stressed, okay, grade 12, I don't know whether you are old enough to have experienced this. Once you are stressed, if you go through stress, you start feeling pain somewhere here, okay? And in general language, we say that pain, you are being strained. The stress is straining you, okay? I am strained. Those are the pain you start feeling there. Old people like myself, we feel that pain. Probably you are too young to experience that, but that pain is the strain. And that strain is caused by the what? The stress. Okay? Here as well with these solid objects, they will also experience strain. Okay? They will also experience strain. For the solid object, it's not the pain. For the solid object, it's the change in their dimension. It's the change in their dimension because of this load now that is coming from outside. Okay? These restoring forces, even though they try to restore, they eventually cause stress. Okay? And then because of this load, the object or the cylindrical rod is going to end up being strained, meaning that its dimension will change. It's going to be strained. It will become longer than it was. Okay? If it's being stretched. Okay? If it's being compressed, maybe something is on top of it here, the load. It's carrying the load. What is going to happen here? This is when it's being compressed. Okay? If it's being compressed, then it's going to get shorter. It's going to be shorter and shorter than it was before. So we say when it changes dimension like that, it's being strained or it's undergoing strain. So you have elasticity, and in elasticity, objects that are elastic will have what? Stress. They will undergo stress, and they will also undergo what? Strain, where they will change their what? Their dimension. Strain can also be calculated, grade 12, using the formula here. Epsilon here is equals to the change in length over the original length. Okay? Very, very, very simple here. You just go for the change in length. Okay? Now, let's talk about the language that they are going to use here for strain. We will look at it when we do the calculations. Now, when they talk strain, right, they are going to say the object stretches by, or they will say the object stretches to. This is what the examiner does, okay? If the object stretches to, for example, the object, here's the object, was 4 meters, and they say now the object stretches to 5 meters, grade 12. That means now they are giving you the new length of the rod, okay, that is undergoing stress. You have the original length, now you have the new length. Or you had the initial length, now you had the final length, because they said it stretches to. Okay? I hope you are with me. But if they say it stretches by, that means already they have given you the change in length. Already they are telling you how it has changed. It stretches by 1 meter. It stretches by 1 meter. Already you have the change. That means you don't have to worry. You can just go straight and take the 1 meter, substitute it here with the original length, and you will calculate your strain. Okay? So the difference is stretches to and stretches by. If they say stretches to, that means we have to calculate your change in length by doing length final minus length initial. In this case, it will be 5 meters minus 4, which is 1 meter. I hope you see here. This is stretches to, and this is stretches by. Okay? Compresses to, compressed by. So let's be careful of the language here. This is what confuses most learners. They don't know when to use the length final minus length initial, when to just substitute here. So I'm saying it's all in the language that the examiner has used. So be careful of the language. If the examiner says stretches to, here's another way you can check. Okay, if they are extending, by the way. Okay, if the thing is stretching, if the second length they are giving you is bigger than the initial length, then it means they are giving stretches too. Then it means you must do length final minus the length initial. But if the length they are giving you is significantly smaller than the initial length, significantly smaller, then it means already they have given you the what? The change in length. Okay? Right. What about the SI unit now? What about the SI unit of strain? Well, since strain is just a ratio where we are looking for change in length, which is measured in meters, over original length, which is also measured in meters, M over M should give you 1. So these M will cancel each other, giving you a strain with no unit of measurement. So it's one of the few things in science that does not have the unit of measurement. So I'm expecting no one to be calculating strain and putting an SI unit. There is no SI unit for strain. You just need its magnitude only. All right. Okay. So then this stress and strain that we are talking about, of them, can be represented in a form of a graph, okay, where we are looking at maybe just one material, like that rod we were talking about, to say the more stress it was, what was happening with its extension, okay? Was it a strain? Was it getting more strained the more it was stressed, okay? All right. Okay, so if maybe you have a material here, okay, and you have stress here, let's say stress here, because the force in Newton will cause stress, right? And then the extension here, that is the same as saying strain. So let's write it as strain here, okay? If you have that material here, and that material is undergoing stress, the more stress the material is undergoing, the more strained the material is going to be. So if you are leaving that load over there, that means the material will continue stretching, right? Over time will continue stretching, okay? So it was found that the relationship between the stress and the strain that occurs there is that of what? Of directly proportional at some point. This is only directly proportional within the limit of elasticity, within the maximum force that can be applied, so that the object can regain its original shape and size on removal of the force, if you remember that elastic limit, okay? Within that elastic limit, the relationship between the stress and the strain will always be directly proportional. So the strain, the object will be strained at the same rate as it's stressed, okay? As it's stressed. So it is strained at the same rate. So it increases at the same rate. I can put it like that. If you remember those relationship of graph from grade 11, the more the stress, the more the strain. The more the stress, the more the strain. But only this happens within the what? The elastic limit. Okay. At that point, it will be what? It will be proportional. Okay. And this we call Hooke's law. This is who found it. Hooke found that within the limit of elasticity, the stress is directly proportional to the strain. It's important that we know this graph and we understand what this graph means. Okay. So this is where we are having the elastic region. So it means here the object is still elastic. Okay. By elastic, what we mean? It means the object is still going to regain its original shape and size when we remove the deforming force. Imagine this object was a spring. You know a spring. If you pull a spring, it goes back to its original position, right? You pull a spring, it goes back. As long as you are pulling it and it goes back, it means the spring is still within its elastic limit, or it's still within the limit of proportionality. It means the amount of stress that you put on the spring, will determine the strain that the spring is going to experience. So they are still going at the same rate. That is what this is saying. But we all know, we've played with those springs. Our spring from the pen, the big pen, that is big. Okay. If you break that pen, you have a spring inside. We've played with them. Okay. We know that those springs are elastic. You pull it, it goes back. You pull it, it goes back. However, we also know that those springs have what is called elastic limit, right? If you pull that spring hard enough, okay, it will reach its elastic limit and go over its elastic limit. So it means at that point, it enters what is called a plastic region. At the point where the spring no longer regains its original shape and size, that spring is no longer elastic, putting large amount of force. The spring will reach this point here. Okay, the spring will reach a certain point, and that certain point is called the what? The breaking point. At some point, if you exert large enough force, at some point the spring will break into two. Okay, that means the spring has went through the elastic region where it was regaining its original shape and size, and then you pulled it with more force. It went over the elastic limit and went to the plastic region where it was plastic. It was no longer regaining its original shape and size. You exerted an even greater force, then it reached a point of no return where it was breaking. Okay, right? So this graph that looks this graph here is very important for you to understand. Grade 12. All right. Okay. Now, if we decide to take the gradient of the graph here, right? If we decide to take the gradient of the graph as it was done in Hooke's law, then the gradient of the graph should be, if you remember, gradient is given by the change in y values or change in x values. So the gradient of the graph here will give us the change in y values, which is the stress, over the change in x values, which is the strain. So the gradient will be the stress over there over the strain. And what this is called, grade 12, is called the modulus of elasticity with the symbol capital letter K. Modulus of elasticity is given by the stress over the strain. And that is the gradient of the Hooke's law graph, or the graph of stress versus what? Strain. The gradient there, when you are checking the change in y values over the change in x values, give you the elasticity or modulus of elasticity. It gives you the modulus of elasticity. This is a value that can be calculated. Grade 12. The modulus of elasticity. It's a value that we can calculate, and it's usually a huge value, or it measures the stiffness of the object. Okay, the elasticity modulus or modulus of elasticity, also called Young's modulus, okay, and it also has other symbols such as E, okay, or Y, but in our examination guideline, K is being used, so we'll stick to K. So this is a measure of the stiffness of the material. Remember, we're talking solid material here, and solid materials have different stiffness. Okay, you're not going to have the same stiff for a huge bar and just a wire rod. The stiffness is not the same there. So the modulus of elasticity measures how stiff the material is. Okay, it measures how does the material resist to be strained. Okay, if the material resists more to be strained, then it will have a higher Young's modulus or modulus of elasticity. But if it resists less, it gets strained more, then it's going to have a less. So that's, you are going to compare them, a spring used in a pen versus a spring used on a gate. Those gates that use springs to bring them back. Okay, or spring that is used in a car. Cars they use spring. That spring is huge. Okay, if you check between those two springs, one spring will have a very small a modulus of elasticity. The other one will have a very high modulus of elasticity. The spring that is more stiff, the spring that does not get strained more, will have a high modulus of elasticity. It will have a high modulus of elasticity. Okay, and then the spring that does not resist more will have a low modulus of elasticity. okay, it will have a low modulus of elasticity. That one it does not resist more. It gets strained very, very easily. Even the formula itself tells you K is equals to stress over the strain. If it gets more strained, then it means this one is going to be less. Okay, if this one is big, this one is less. As you can see, they have a relationship, an inversely proportional relationship there. So if we have more strain, then it means we have less modulus of elasticity. But if we have less strain, it is strained less, then we are going to have high or more modulus of elasticity. Okay, now, great work. Let's talk about how they are going to usually ask these questions, okay, in the exam. Usually in the exam, grade 12, they are going to ask this question by saying, start by calculating stress, calculate strain, and then calculate the modulus. Okay, these usually going to be 4 marks, 3 marks, 3 marks, free 10 marks, free 10 marks, grade 12. Ensure that you do not lose anything here. You take all these marks. As long as you know your area formulas, as long as you know how to convert, this should be very, very, very simple. And then you are able to define, because before they say calculate here, they're going to say define. And in these definitions, the ones that I've counted, one of them is going to be asked. I unfortunately do not know which one. So that means we must know all of them. It could be Hooke's law, it could be strain, it could be stress, it could be deforming force, it could be perfectly plastic body, elasticity, plasticity. It could be any of those ones. So we must make sure that we know all of them and we are prepared. All right. So to show you what I'm talking about here, I'm going to just go through a previous question paper question with you very, very quickly, and then we'll look at what is it that we are talking about, or how we would make sure that we collect all the marks here. Right. So it's a previous question. It was question 5. It says one end of a wire, which is 2 meters in length, is attached to the ceiling. Okay. So there's a wire attached to the ceiling. Okay, like I was saying, it has a cross-sectional area in the form of a circle, okay, with a diameter of 3 millimeters, right? You'd remember grade 12, okay, because all of you, I am sure, are doing EGD. In engineering, graphics, and design, usually when they want you to draw a circle, they usually do not give you the radius, they usually give you a diameter like this, see, and then they say 50 millimeters. This is what they usually do in engineering, graphics, and design. And what do we do every time before we draw the circle that they want us to draw? We take the 50, we divide it by 2, and we get 25. That is our radius. So we must always remember that radius is the diameter divided by 2. So this is what they are talking about here. Very, very important to remember. Okay. They're saying an 80 kilogram mass piece is attached to the other end of the wire. This is the end of the wire. This is our load. 80 kilograms mass piece attached there at the end of the wire. Due to this, the length of the wire is increased by, 4.4 millimeters, which is significantly smaller than what? Than 2 millimeters, okay? So that means they've already given us our change in length. So the mass piece does not touch the floor. So it means the mass piece does not touch the floor. So it means it keeps on exerting that force there on the rod. Okay, question number 1 says, define the term stress in weight. And what you say stress is in weight, we say it is internal restoring force per unit area of a force. That means I need to calculate my what? My area. Okay, so what do? I go on the side and I calculate my force. Where is the force? The force here is going to be exerted by the weight of this 80 kilogram mass piece. So I simply need to say W is equals to mg, where mass is 80 times 9.8, and I get the answer. And then I'm going to quickly calculate that. 80 times 9.8. Then the weight there is 784 newtons. I hope people are working with me there. Okay, all right. So I now know the force. Now I need the area. Okay, I'm going to calculate the area within the question itself, grade 12, because I'm avoiding this issue of pressing my calculator a lot of time. Okay, but before I do that, I'm going to fix this issue here. Diameter. My diameter is given as 3 millimeters. One, it's a diameter. That means because I know the area of a circle, they said it is a circle here. Okay, where is it? Cross-sectional area in a form of a circle. So the area that I'm talking about here is the area of a circle, which is pi r squared. It is pi r squared, the area of a circle. So it means I need the radius. I'm given the diameter. So what do? Radius is given by diameter divided by 2. Okay. And then what is my diameter? My diameter is 3 divided by 2. All right. And the 3 divided by 2 will give me 1.5. Okay, just making sure there. But it's 1.5 millimeters. I do not want to forget that, because I still need to convert that 1.5 millimeters to meters, grade 12. So I now convert it. I write it as 1.5 times 10 to the power minus 3. It is already converted if I write it like that. It's already converted. 1.5 times 10 to the power minus 3 is the radius in meters. Then I can now come here and substitute. Force, I know the force is 784 newtons over the area, which is pi r squared. I know that it's pi times the radius, which is 1.5 times 10 to the power minus 3 squared. Okay, and then I go to my calculator. I want to press my calculator, not a lot of time, to avoid the issue of rounding off. Okay, so I don't want to press a lot of time. So I'm going to say 784 over, on the calculator, I don't say 3.14. I do not say 3.14. I say shift there, or second function, and then I say press the sign of pi. Pi will appear on the calculator. Open the bracket, 1.5 times 10 to the power of a negative 3. Close the bracket, square that. What is my stress? A huge number, 1109,13311.5. And the SI unit should be Pascals. Okay? Or another person will write Newton per square meters. From now on, I'll be writing Pascals. Newton per square meter is fine. Okay? Right. Let's one again, grade 12. Okay, some of you will find these answers, they will come from the calculator in scientific notation. It's fine, write it as the calculator is giving you the answer. But if you get it in an ordinary value like this, my advice is that do not change it in scientific notation unless you are sure of the scientific notation that we learned in grade 12. Okay, right. And then 5.1.3 is asking us to calculate strain. This becomes very, very simple. Calculating of strain. Strain is the change in length. Let's fit it here. Strain is the change in length over the original length. What is my change in length? My change in length is 4.4 millimeters. So that is 4.4 times 10 to the power minus 3. That's me converting from millimeters to meters. The conversion is very, very important, grade 12. Over the original length. The original length is simply 2 meters. Okay, why is it that we did not do length final minus length initial? Because they said it increases by. That's the language issue. It did not increase to, it increases by this much. So that's already our change in length there. So 4.4 times 10 to the power of a negative 3 over the original length. And then the answer there, they say, is 2.2 times 10 to the power of a negative 3 with no SI unit. 3 marks taken, and I am fine again. Right. And then the wire's elasticity modulus, or the modulus of elasticity, which is the last one, as I said. Stress, strain is modulus of elasticity. Stress, strain, modulus of elasticity. Okay? Even though it could be a mixed, okay, they can change where they maybe give you the modulus of elasticity and the strain, and they want you to calculate the stress, but they are always going to play around those formulas, great off. All right, so what do I do in that case? I simply say K is equals to the stress over the strain. And then what I must do here, and I must always ensure that I do, is that I use these values, okay? No matter what, grade 12, use the values that you have calculated. Trust me, you must use the values calculated in the previous questions. Even if you realized that there was a mistake somewhere here, if maybe there was no time for you to fix that mistake, use those values, okay? Don't try to change things, all right? So the stress here is 1109,13311.5 over 2.2 times 10 to the power minus 3. And then this, again, I expect is going to be a big number as well. 0.91331.5 over 2.2 times 10 to the power of a negative 3. I get my answer as 5.04 times 10 to the power of 10. And what is the SI unit of Young's modulus? Let's check now. If we say that the SI unit of stress, is Pascal, and the SI unit of strain is no SI unit, which is basically 1, then the SI unit of Young's modulus should be Pascals over 1. And anything over 1 remains that the SI unit there should be Pascals. Okay, I hope people get that. So the SI unit of Young's modulus is Pascals or Newton per square meter. Okay, all right. Let us continue again, grade 12, by the issue of SI prefixes here. SI prefixes here, they become very, very important, grade 12, in this topic again. The issue of knowing your big numbers, okay? Your kilos, your mega, your giga, and your tera. I always say, people, you're buying data daily, okay? You must know these things, okay? You've been talking about kilobytes. At some point, you talk about megabytes. At some point, you're talking about gigabytes. At some point, you're talking about terabyte, right? Okay, so we must be familiar with these things. So we must know the numbers, okay? To say kilo is times 10 to the power 3, mega is times 10 to the power 6, and then we say giga is times 10 to the power 9, and then we say tera is times 10 to the power of 12. So this is kilo. If they give you the number in kilo, this is mega, and then this is giga, okay? And this is tera. Grade 10 stuff. Please, grade 10 stuff. Remember those things. They might give you values in kilos, in megas, in gigas, and in teras. Let that not be something that is going to stop us from collecting all these marks, okay? So we know these. We must also know the smaller ones, the milli, the centi, okay? We must know the micro, the nano, and also the pico. We must also know they all go in 3, except for the centi, which is a 2, okay? Last question there is just simply asking for 2 examples of practically perfectly elastic bodies, okay? Practically perfectly elastic bodies. You can give us any perfectly elastic bodies. You can talk of squeeze balls, right? Those stress balls that you squeeze, and then you can talk of springs that are perfectly elastic there. Any example that you can give us that is perfectly elastic is fine. Those are just practical examples, okay? Right. Without any wasting of time, let's move on, grade 12, to our next topic, which is viscosity. Okay, right. When we talk viscosity, grade 12, we say viscosity is the property of fluid to oppose relative motions between the 2 adjacent layers. The property of fluid to oppose relative motions between the 2 adjacent layers. But I said, to better understand this, yes, when we define it with definition from the examination guideline, but to better understand, when we talk of viscosity, we are talking about how easy or how difficult it is for the fluid to do what? To flow. In this case, our fluid will be the liquid, okay? So how easy or how difficult it is for the liquid to what? To flow. That's your viscosity. Let's compare water. You take water, water flows easily. Compare it to cooking oil. Cooking oil does not flow as easily as water. So when you compare the two, the other one, cooking oil, will say has more viscosity, okay? And then water has less viscosity. Take the cooking oil, compare it to honey, for example. Honey is going to take even more time to flow compared to the cooking oil. So honey has more viscosity. Honey or cooking oil has less viscosity when compared to honey. Okay, so it's very, very important that we remember all of that with regards to what? To viscosity. We must also remember the effect of temperature, on viscosity. Okay, things that we've touched on again when we were looking at organic chemistry, their intermolecular forces. The viscosity of liquid decreases with increase in temperature. I always make this example for you, which I'm going to make quickly before I move. You want to fry a pan, you want to fry an egg, you want to fry an egg, you are going to use a frying pan if you want to fry an egg most of the time, right? When you do that, you're going to pour your cooking oil there. But what you would notice with your cooking oil as you pour it into a pan there, it does not move as quickly as you would like it to. So it moves, and it moves very slow. Why? It has high viscosity compared to water. It will not move as quick as water. But once you take it and you put it on the stove there and you wait for it to heat up before you can fry your pan, and then if you just decide to take your pan and shake it, what you would notice is that the cooking oil starts moving and spreading all over the place quicker than it was before you heated it up. What has happened? It was the effect of what? Of temperature. The high temperature has made the viscosity to decrease. Okay, so the high temperature of that that you put there in that cooking oil has made the viscosity of the cooking oil to do what? To decrease. We say it has made it to be thin. Okay, those are the words that the terminology that is used. Thin. Okay, when it's thin, it's when it has less viscosity. Okay, so it has made it thin, it has less viscosity. Before, we say it was what? It was thick. That's the terminology that is used. When it is thick, that means it has more viscosity. Has more viscosity there. So there is thin, less viscosity, thick, more viscosity. Thick, difficult to move, resist is more. Thin does not resist that much, moves easily. So when you start with the cooking oil, you start with it being thick, all right? And then you put it on top of the stove, it gets heated up, increase in temperature. When you increase the temperature, the viscosity will decrease. That's what is being said here. The viscosity of liquid decreases with increase in temperature. Then now the cooking oil is spreading all over the frying pan. It moves as quickly as possible. That viscosity is less viscous. All right. Okay. Motor oil. Okay. Viscosity, motor oil. Viscosity refers to how easily oil pours at specified temperature. So when we talk in terms of application of viscosity, grade 12, we look at motor oils. Okay. Those motor oils, it refers to how easily they pour. Some motor oils pour easily, some motor oils do not pour easily. Are we together? Right? So thin oils, we say they have lower viscosity, while thick oils have higher viscosity. What I was quickly saying there. Right. When talking more about motor oils, we'll have to quickly just compare between mono and multigrade oil. Okay, so we have what we call is monograde oil. What are monograde oil? These are grade oil that are graded by the SAE. And what is the SAE? That's the Society of Automotive Engineers. An important term to know, okay, because at some point it was asked in an examination. SAE stands for Society of Automotive Engineers. Okay, they grade oils differently. Okay, so if it is a monograde oil, it means it is graded to function, okay, or it is graded according to its viscosity, that it functions only at that viscosity. If it's a thick oil, it's a thick oil. If it's a thin oil, it's a thin oil. It has only that grading. Are we together? So that means that if you heat this one up, okay, it will become thin. It will not act a different way. Unlike a multigrade oil has act in sort of two different viscosities, okay, right? A multigrade oil will act as a viscosity of 10, or it can act as a viscosity of 40, like this one, 10W40, okay? So when does it act as a viscosity of 10? It acts as a viscosity at 10 at a temperature of 0 degrees, 0 degrees Celsius, meaning at cold temperatures, okay? At cold temperatures, this oil flows lighter at startup. It's light, its viscosity is low, it's at 10, okay? That's why it is accompanied by a W here. The W stands for what? Stands for the winter, okay? And then at high temperatures, it operates as a 40. We say there, this is measured at 100 degrees Celsius. That's at high temperature. It operates as a 40. So these multi-grade oil are used where by cars where they have changes in their temperature, or there's a change maybe in the atmosphere. There's a change of seasons. Maybe we are going from winter to a summer season, right? So if you have a multi-grade oil, you don't need to be changing your oil there, because even at summer it will be able to function there, because even if it's winter, let's say it's winter, you are coming from summer. If it's winter, it will be able to go to 10 in the morning while it's still cold, right? But then when the engine heats up later on in the day, as you keep on driving your car, it will now start functioning as a what? As a 40, okay? And it's important that we know that this W stands for winter, grade 12, okay? Right, so that's it with viscosity there. Very important to be able to define viscosity. Very important to know the effect of temperature on viscosity, and very important to know your monograde oils and your multi-grade oil. Even though we are not going to details here, grade 12, because of the issue of time, but this is what is very, very important for us to just understand there. All right, now let's look at hydraulics, okay? We say hydraulics is the study of mechanical properties of liquids, okay, and how they help us. But for us to study hydraulics, we must look at thrust first. What is a thrust? We said that is a normal force. It is exerted by a liquid at rest on a given surface in contact with it. What are we saying? If you have a liquid here, and then you enclose the liquid here, a container, enclose the container, and it has liquid. This liquid will exert forces perpendicular to surface, okay? These forces will be exerted in all these directions, but all of this direction will be perpendicular. Hence, it's called the what? The normal. As I've said before, the word normal refers to perpendicular to us. So they are going to exert forces that are perpendicular. And these forces that are perpendicular, remember, it's a force. And if you maybe can boil a squeeze bottle, you boil it there, what you would notice is before it bursts, it will expand, gets bigger. That's the force we are talking about there. That's the thrust that we are talking about there, grade 12 there. That thrust is causing what we normally say is pressure. And we say that correctly. It is pressure, okay? What is pressure? It's the thrust acting on the unit area around the point. Do we know the definition? If yes, that's important. Let's know the definition, and then the definition of thrust. And then we must understand that when we're talking pressure, we have pressure for liquids. This is pressure for liquids. And then we have general pressure. Let's call this one general pressure. It's pressure for just, it could be solid and also other fluids such as gases, okay? But pressure for liquid is calculated using this formula here, where we have P is equals to the density of the material multiplied by the gravitational acceleration and the what? And the height. So that tells us the pressure of a liquid depends on the height, okay, or the depth of that liquid, okay? How deep is it? The depth of the fluid or the liquid, okay? And the density, it also depends on the density of the liquid. You don't have to worry about densities, because density of each liquid that you could be asked of will be given to you. What is important is that you are able to use this formula to calculate. One of the easiest formula to use. Okay, pressure in general is given by the formula P is equals to force over the area. The issue of area comes back to us yet again, grade 12. The issue of area comes back to us. It is important that we know area of shapes like the circle, area of the square, the rectangle. We are able to convert from millimeters to meters and all of those things. Very, very important. Without wasting time, let's continue them and go to Pascal's law, right? What does Pascal's law state? Pascal's law says in a continuous liquid, the pressure applied at a point is transmitted equally to the other part of the liquid. Very important, grade 12, to know this law. You must know this law, you must sing this law. But what does this law say? The law says to us, if I have pressure 1 here, that is caused by this force, the thrust, okay? There is the thrust here causing pressure. So there is a pressure here. What it says that the pressure that will be here will be transmitted equally to the other part. So if the pressure that was here was equals to 40 pascals, for example, it means the pressure here will also be equals to 40 pascals. It means the pressure here will also be equals to 40 pascals. It means the pressure this here will also be equals to 40, but it is transmitted equally to the other parts of the liquid. So the pressure that was here will be transmitted, will be the pressure that is also here. Meaning that P at 1 is equals to P at 2. But we already know that P is given by the formula F over A. So that means for P1, that is F over A, or F1 over A1 equals to F2 over A2. Now this formula can be manipulated in all different types. Grade 12 can be manipulated such that it now gives you F1 over F2, A1 over A2. It can be manipulated in different ways. So be careful. The examiner likes manipulating this formula and ask you about it in the multiple choice question. So I want you to just, in your spare time, try to play with this formula, manipulate it as much as you can within the rules of mathematics, of course, okay? But the formula that will be given in your data sheet will be this one. F1 over A1 is equals to F2 over A2. I advise that people always start with P1 is equals to P2 before they say this, because that is where the law starts. The pressure at this point is transmitted equal to the other part of the what? Of the liquid, okay? So what can this help us with? Well, in hydraulics, this helps us with, if I have a small amount of force that I exert here, given that my cylinder or my piston here has a small area, very, very important that the area is small here on the first piston, the pressure will be equal. If the pressure it will equal, it will output a larger force. It will output a larger force. And how does that help us? Well, that helps us to lift heavy things. That is going to help the dentist to lift you with his chairs by simply using his foot. The dentist, if you've been to the dentist, you will see that there's a chair there where the dentist just simply press with the foot there and it moves you up, it moves you down. What is the dentist using? Hydraulics there. Okay, there's a piston that is small, the smaller piston there, that's where you exert a small amount of force. That small amount of force will then transmit a force that is equal all over to the point where you have a what? A greater or a bigger area. Now, once you have a bigger area, the bigger area will output a larger force. That's why the dentist is able to lift you. That's how the trucks, they are able to brake, because most trucks are using hydraulic car brakes. You are able to brake a huge truck by simply using your feet. Okay, you brake it by applying a force on a smaller area. Then you have pressure transmitted in a continuous liquid at equilibrium, and then it gets to a larger piston. That larger piston will output a what? A larger force there. Grade 12. Okay, right. So with that in mind, you get things like car brakes, hydraulic car brakes. You get hydraulic car jacks. You lift a heavy car up by using that. You get also forklifts. Okay, these are uses. These are things that you must also know, by the way, grade 12, uses of hydraulics. These questions, they ask them. Forklifts, okay? Forklifts, okay? Dentist chairs, okay? You get bulldozers, okay? These are all things that you got. Hydraulics, car jacks, Okay, these are all examples of the uses of these hydraulics that I wanted to make sure that you know before you enter the examination. Okay, so again, simple here, you'll be asked to do calculations here, and you'll be asked to do questions. So let's go through some of the questions and see if we can be able to answer them quickly. Right, question 6 here says the diagram below shows a hydraulic lift. Okay, a force F1 of 250 Newton is exerted on piston 1, which is the smaller piston, with a circular area. They tell us that the area is circular. Very important for the formula. It means pi r squared. Okay, the radius of A1 is 2 centimeters. We have a radius which is in centimeters, must be converted 2 times 10 to the power minus 2. I've converted already. Piston 2, which is a circular shape, has the area A2 of 6.158 square meters. This one, no need for me to convert anything here. Right? State Pascal's law in weights. I'll just simply state it. In a continuous liquid at equilibrium, the pressure applied at a point is transmitted equally to the other parts of the liquid. Okay, calculate A1, which is area 1. How are we going to calculate A1? We're going to say A is equals to pi r squared, the formula. Then we are going to say pi. What is the radius? The radius is 2 times 10 to the power minus 2, already converted like this. Or someone will say 2 divided by 100. That is up to you. Then do not forget the square. Then you go straight to your calculator. Pi 2 times 10 to the power of a negative 2, square that. You get that your area is 1.256. Let's make 3 numbers after the comma because it's 3 numbers after the comma here. Square meter. Okay, square meters there. And then they say calculate F2, the force that is going to be outputted here, the force that we expected. It must be a bigger force. All right, how are we going to do that? What we know is that Pascal's law tells us that the pressure here will be transmitted equal. So P1 is equals to P2. All right, that means F1 over A1 is equals to F2 over A2. What is F1? They tell us with the input force is 250. What's A1? I just calculated it as 1.256 square meters equals to F2, I don't know, over A2, they say is 6.158. And then from here, I simply need to work out my maths and work out F2. How do I do that? Cross multiplication. So 250 times this is going to be 250 multiplied by 6.158 equals to F2 multiplied by 1.256. Right? Hope everyone is working with me there. To get F2, I need to divide by 1.256, divide by 1.256. Right? Continue here. F2 should be equals to, right, 250 multiplied by 6.158, close the bracket, all over 1.256. What do you get there? You get that F2 is 1,225.72 newtons, which is facing upwards. The direction of the force. So that's how much force that we are going to be having there. Let's look at 6.3 there, which says the distance between the 2 points is decreased by using a shorter pipe. How will it affect your answer in question 6.2.2, right? Only increase, decrease, or remain the same. The answer there, it will remain the same because the distance between the piston cannot affect the pressure. Okay, the distance between the two does not affect the pressure, and it will not therefore affect the output force there. The output force can be affected by the area, can be affected by the area. The area is decreased or increased, that will affect the output force, not the distance between the two pistons here. So if we shorten this pipe here, it will not affect my answer whatsoever. Okay, 6.4 says there, name 2 uses of hydraulic system. Well, we've named a lot there, forklift, dentist chairs, hydraulics car brakes, hydraulics jacks, bulldozers. You can name a lot. Okay, just make sure you go to exam knowing at least 4. Make sure you go to exam knowing at least 4. Okay, so that's how you are expected to do these calculations, Kretov. Again, as you can see with the calculations I've done, the most important things was I'm able to do the area calculations, and I'm also able to convert between units. If you are able to do that, you should be fine. All right. So grade 12, I'm going to give you just 2 minutes to go through this activity, and then we'll go through it together to see if you are able to answer these questions. Okay, your time starts now. Welcome back, Reto. I hope 2 minutes was enough for you to quickly answer those questions. The 2 minutes because we do not have a lot of time there, grade 12. So let's just go through the questions. It says modern engine oils are specially designed as multi-grades. Okay, a mechanic has to choose between 2 motor oils, a 10W40 or a 5W40. Define the term viscosity. Then we say it's the property of fluid to oppose relative motion between the 2 adjacent layers. Then what does W in 10W stand for? Well, the W in 10W stands for winter. These are typical questions that could actually be asked. Grade 12. Very, very simple. W stands for winter. Which one of the 2 motor oils should the mechanic choose for a winter season? Which one of the 2 oils should the mechanic choose for a winter season? Should they choose a 10W40 or a 5W40? Well, they should choose a 5W40. The answer there should be 5W40 for a winter season. Why? Because in winter, you want a thin oil. You want thin oil at startup so that the thin oil can move through the pistons as quickly as possible. It does not take time. Remember, thicker oil or thicker liquids move slower. So you want a thin oil such as a 5 when you are in a winter season compared to a 10. And you would notice that both of them, when the engine starts heating up, they function as what? As a 40 or rated as 40, their viscosity. So you would prefer to have, a mechanic would prefer to take what? A thinner one at start up and a thicker one, and it gets thicker when the engine heats up. This is because if you use a thicker one, it will take time before it reaches the pistons of the engine. And if it takes time there before it reaches the piston of the engine, that might damage and cause some wear in your engine. How does temperature affect the viscosity of liquids? Well, as we've said before, the viscosity of liquids decreases with an increase in temperature. So those are just some typical questions that could be asked when it comes to viscosity. Okay. Right. Let's just go through the summary of our lesson, grade 12. Okay. We said we want people to be able to define stress. Okay. But not only define stress, we want people to be able to calculate stress using the formula force over area. Okay. And very, very important, grade 12, cannot emphasize this enough. You must be able to convert between units. You must be able to calculate the area of the following shapes. Pi area is pi r squared for the circle. Area is then times breadth for the rectangle. Area is side squared for the square. Area is half base times the perpendicular height for the triangle. I've never seen this one asked before, but I cannot say it will never be asked. However, I've come across questions where these ones have been asked before. So it's important that you know these formulas. It is extremely, extremely important that you know these formulas, grade 12. You must be able again to convert from millimeters to meters, from centimeters to meters. Very, very important. From square millimeters to square meters, from square centimeters to square meters. Again, questions that I've seen being asked before by examiners. So you must be able to do that. You must be able to define the term strain and must be able to calculate the strain, which is the formula change in length over the original length there. Okay, you must be able to state Hooke's law, all right, and then you must be able to calculate the modulus of elasticity, which is K is equals to the stress over the strain, grade 12. Very, very important. Easy marks there. If you know definitions there with elasticity, know your definitions, and you know how to use these three formulas, and you know how to convert and calculate your area, I promise you that you will take all marks, not most, but all. I can promise you that you know your definitions there, and you know how to work with these formulas, and you know how to do the areas and do the conversion. I promise that you are going to take all those marks. Calculate the stress, strain, and modulus of elasticity. Define viscosity. People must be able to define viscosity and be able to discuss the effect of temperature on viscosity. And you must know your multigrade oil 5W40 versus a monograde oil W, a monograde oil SAE maybe 30. Okay, and these are also SAEs. Okay, you must know what the SAE stands for, Society of Automotive Engineers. Okay, you must also know that, and you must be able to compare, and you must understand that this first number here is the viscosity at startup of the engine, the viscosity at cold temperature, the viscosity at 0 degrees Celsius. Understand here that this is the viscosity when the engine is heated up or is heating up, the viscosity at 100 degrees Celsius, the viscosity in conditions on hot conditions. Okay, you must understand that. And you must understand that here in a monograde oil, it's just the viscosity. If it's thick, it's thick. If it's thin, it's thin. And it's not going to change depending on the conditions. Okay, if it's going to remain like that, it will just change based on the effect of what? Of temperature. So you're not going to have it changing its viscosity, functioning as a better viscosity because of temperature. Instead, it will become thinner and thinner if the temperature increases. You must also be able to state Pascal's law, right? In a continuous liquid at equilibrium, the pressure applied at a point is transmitted equally to the other parts of the liquid. And you must also use Pascal's law to calculate P1 is equals to P2, F1 over A1 is equals to F2 over A2. If you can do the stress and strain calculations here, this becomes take and go. Take a farm by grade 12. There is no way you are going to fail this one. This becomes extremely, extremely easy. Take and go there. All right. So here's our homework there. I want you to go through and try to answer these questions here, where you can see here. I just want to take your attention here. The stress here is given in MPa. That's megapascals. That's what I spoke of there. Numbers can be given in mega. That's megapascals. That number must be converted that number that you are given there from megapascals to pascals by using the relevant conversion there. Okay, and then you are given the area there, and then you are also given the change in length here. So you should be able to calculate, as you can see, the examples, the question is easy. They say define stress, state Hooke's law, verify 4 marks for spring. Calculate the force that causes the spring to stretch. You are given the stress, you are given the area, you can calculate the force. The strain, you are given the original length, you are given what it increases by, you can calculate that. Elastic modulus, you have the stress, and then you have the strain, you get elastic modulus. Full marks, 14 marks for free. Okay, the second part of the homework talks about pressure, and I made 2 identical holes at point 1 and 2 in a plastic container filled with water as shown in the diagram. You define the term pressure, which we've talked about. Is the pressure of water at point 1 greater than, less than, or equals to the pressure at water at point 2? Explain your answer. We've spoken about the pressure depending on the depth and the height there, with the formula P is equals to density GH there. We've spoken about that, and you can give the explanation. Why is the water from the hole at point 1 forced out further than the water from the hole at point 1, at point 2 versus point 1? Again, all speaking to pressure there. See if you can be able to answer those questions, right? Then there's question 7 here, which is again Pascal's law. Right, try to answer those questions there. You are simply stating Pascal's, and they want you to calculate the force that must be exerted in this case. So F1 over A1, F2 over A2, you are calculating for F1 this time around. How are you going to get F2? You are given the mass. Remember here, this is what we are lifting up here, is the mass, is the weight of this car. So W is equals to mg for those of you who don't know. And for those that I'm spoiling for them, I am sorry, but I'm trying to help the rest. 1,200 times 9.8. So try to do those questions there. And if you get stuck there, you can even go to your teachers there, and I'm sure they are going to help you a lot with that. These topics that we've combined here, those are 3 marks grade 12. Ensure that you understand everything when it comes to this. And it's mostly the definitions, and the calculation using of formulas. Just know the definitions and use the formulas there, and know the area formulas. Please, important. Know the area formulas, know how to convert, and know that the radius is the diameter divided by 2. People who do EGD, that should be common knowledge to you. All right, grade 12, please make sure that you join us on the 12th of June 2025, as we'll be doing the revision of the whole paper 1 in trying to prepare for the question paper that will be written the following day. Okay, right? And then we do all topics that have been covered from first term, revision first term up until the second term, trying to prepare for the paper, and we'll be checking them which sections can we collect most marks on. Especially we'll be looking at mechanics there, which is one we have looked at a lot. So join us there on the 12th of June 2025 as we prepare for paper 1. Make sure that you are here. Grade 12, thank you.